Welcome to exploring PASCO OpenSciEd chemistry. Why are you supposed to get away from water when there's lightning nearby? This is a little preview of the OpenSciEd curriculum in PASCO form or certified PASCO version. Today's goals are to get the feel for a lesson in OpenSciEd and also get the idea of how a unit works. This unit embraces the student-driven storyline instructional approach. You'll see an example of how PASCO has infused technology into this unit, and it's just an example of what could happen in any unit or lesson in the curriculum. We are also investigating how increasing the concentration of salt in water affects the rate of charges flowing through it. So you'll also see how we support teachers with equipment kits and resources and how it's organized and delivered in PASCO Portal. So I'm going to talk about all those things. We're specifically looking at Unit C2. And the goal of Unit C2 is to understand the anchoring phenomena of lightning, something that everybody's got experience with. What is lightning? Where does it come from? Why is it dangerous? How do we stay safe? All those questions we want to be able to answer, but in order to be able to answer those questions, you have to learn what's happening at the particle level in terms of not only just matter, the particles, but also the forces among the particles and the energy transfers among the particles and among systems and between systems. So this lays the foundation for a really strong understanding of chemical bonding and other concepts in future units in the chemistry course, in addition to future course physics as well, and also blending in some content from biology and things that were learned in middle school. So let's jump into lesson one. We're going to, as a class, experience the anchoring phenomena together. So here we are in the first lesson. Now, I want you to watch a video. So in a second, you'll see this video, and I want you to think of these two questions as you're watching the video. What's happening in the video? Number one. And number two, obviously it's going to be lightning. Where is the lightning going from and to? And let's play that video. So keep these questions in mind while we go here. There's no sound in the video, so you're just focused on these two questions and watch. Looks like it froze. There it goes. Where is lightning going from and to? What's happening here? Can you tell? It's kind of hard to tell, right? I mean, it's going so fast. Wouldn't it be great if we could slow down that video? And it just so happens that I do have a video of slow motion lightning, but we're not just going to watch it. Okay, go ahead and watch it once. It's an animated GIF. But uh, we're going to write down this time what we notice and wonder. So grab your piece of paper, grab your pen or pencil, and make a T chart on your paper. Just like this, write notice in the left column and wonder on the right column. And be ready to share with your classmates what you notice or what you wonder when you see the slow motion animations of lightning occurring here. And if you want to, you can also add in whatever you saw in the last video. But focusing on this one, what do you notice and what do you wonder? I'll let it go a couple more times. Write down anything you notice. What do you wonder? This is the same bolt on a loop. Okay. So as you finish writing out your last noticings and wonderings, if we were doing this in classroom, we would spend a lot more time letting students think and write about it. But for the sake of time, let's move on. You are going to share with class. So here's how we're going to do that together today. Grab your phone and scan the QR code, or Roger's going to paste the link into chat. So if you want to, you can also go on your computer and get into that Padlet, and please type in your noticings or wonderings, at least one, either one noticing or one wondering, or both, or more than one. But go ahead and post your noticings and your wonderings, and I can see you all there on the Padlet. And here's what it looks like right now. It's blank, but we're starting to see some responses. The busy moth, and by the way, these are anonymous responses. Busy moth says some parts of the bolt are more branched than other parts. The clever puffin says sky to ground on this strike. I see some other folks are typing. It looked like the flash was brightest when the lightning hit the ground. Lightning originates from a similar point each time. We got some wonderings here. What is a flash made of? Good question. Do all strikes branch this much? Noticing the bolt seems to travel from the cloud to the ground. So here are some responses. Okay, I'm going to give you about 10 seconds to get your last thoughts in there. Was it actively raining when the lightning struck? Is lightning just energy, or is it also matter? Energy and matter. We're in Unit C2 in chemistry. We just studied in C1 all about matter, and we have some prior knowledge, and now we're starting to think of that knowledge in a different context. And why didn't all the branches reach the ground? Okay. Does lightning always start in a cloud and travel to the ground? Does it ever go the other way? Great question. So you can see how this phenomenon that everybody has experience with, and then if you haven't seen lightning, we can create an experience for you. Everybody has something to say here. So that's great. When you give everybody a voice and everybody has something to say, this leads to more ideas. And this is great in science. We have different ways of knowing, and together we generate different ideas and we can explore these ideas and maybe come up with some new understandings that we couldn't have arrived at otherwise. So at this point, everybody's shared their noticing and wonderings, and we continue with discussion. Now we take it from the whole class kind of sharing their ideas and noticings and wonderings, and now we tell the students, hey, turn to each other, do a turn and talk, find a neighbor. What do you know about lightning? What stories do you know about lightning? What that are shared in your family, or some mythology you learned about all around lightning? And they might say, like, oh yeah, there's the god of lightning and thunder, and or my uncle was struck by lightning when he was sitting on a toilet. That's terrible if that happened, but lightning has struck toilets. How did that happen? How do these stories make sense of the lightning and its role in the world around us? So students talk to each other. Notice the teacher is not teaching as well, the teacher is leading learning. So the teacher's not up lecturing, students are driving the learning here. They're coming up with the questions, they're coming up with the observations, they're talking to each other, they're telling what they know, and that's really what's driving the lesson forward. Not just in lesson one, but in the entire unit. So moving on, next, after that discussion occurs, we bring the class back together, and then we share data and students, and this is actually 3 different assignments, and I'm going really fast because we want to cover as much as we can. We got to get through an entire unit here. So a few different sources of data, students start to notice patterns. They can see, look at these graphs organized from the beginning of the year to the end of the year by season, by month and weeks of year. And students will notice, hey, the middle of the year is always the highest number of flashes in millions of flashes. Why is that? Well, it's warm. Okay, what about the number of flashes per year in the United States alone? Well, the highest seems to be where it's hot and humid in this region, and then over here in the West Coast, where there's a lot of mountains and stuff, it seems to not happen as much. And another pattern we see emerge in the world is, wow, remember that line that we call the invisible line that we call the equator? It turns out there's a whole bunch of lightning, and that's the highest concentration of lightning is through the equator region. And as you go towards the poles, it's less common. So we see patterns with the data. Again, students are finding these patterns. Students are driving the learning here. And then not only do they notice the patterns, but it makes them wonder why. Why? Okay, what's commonality among these things? Okay, we see high temperature and water. Let's talk to each other and come up with a model. So we want to quickly review, how do you do a model? How do you create a model? And students would have had experience with this already from Unit 1. But you would want to remind students the things that need to be included in a model and remind them that they should be showing relationships, not just the pieces, not just the components, but how they are related to each other as they start their initial beginning model. And it's expected that there's a lot of questions and unknowns. We're just trying to make sense of what we saw with only what we know now. And we're going to arrive at a new understanding. And we know that slowly and slowly we're going to change this model as we get new information. So students would initially create a model and then talk to each other about what they put in their models and then iterate, add more and modify their models based on their conversations. And then on their own, go back, revise the model. Now add a little bit more complexity to it. Make sure that you're adding arrows with energy transfers. In this example here, students should be labeling with matter energy using colors and arrows to show energy transfers. And then continuing, the idea here, this is already at the end of day 2, students have enough to be able to come together as a group and share ideas together and say, hey, we've talked to each other, we've thought through things, and now we have these pieces, these places where we agree or disagree or things that we don't know. And then we make sure that we record these ideas. And at this point, at the end of day 2, there's an opportunity for the teacher to collect students' work and look at their models and give some initial feedback. So throughout the lesson, students are getting feedback from their peers and from the teacher. And so they're just starting to learn. It's a way of formative assessment. And here's just a zoomed in picture of the class consensus model. Now, maybe to your individual model, you might have added more systems, and the class together can come to agreement on what things absolutely have to be in the model. Like the ground really needs to be there, rain needs to be there, we think it's always there, they need to be clouds, and so on. Then on day 3, you take the everything that you've discussed on the previous couple of days, and students continue discussion. And the idea here, we create a poster called Related Phenomenon. This is one of the big components that you always see in opening lessons in every OpenSciEd unit. So the purpose of the related phenomena discussion is for students to connect their engagement with lightning, their engagement with that anchoring phenomenon with their own experience. So that's what related phenomena are. What about lightning? What about something similar to lightning? What signals do you use to decide to protect yourself against a storm? How does where you are determine how you stay safe? Some questions about things that are not directly lightning, but related to lightning. And those continue to drive forward the questions that we decide we want to answer. Some we will answer, some we don't. So after you go through the related phenomena, in this lesson anyway, you build the driving question board. And this is where students take all of the questions that they still have that they've created over the last 3 days, they write them down on a sticky note, they initial on the back, and they take it up to the front of the class. And everybody participates here. Everybody has value. Everybody's opinion is valued, or question rather. And then you start to see patterns emerge. And you can put these questions into categories. And then these questions are really what drive forward the rest of the lessons with direction from the teacher. So another poster that comes up early in the unit, like in lesson 1, the ideas for investigation poster. Students not only drive the learning, but they also plan the investigations and determine ways to test their ideas. So you work together with your partners, your elbow partner, and with different people, and you think about, well, what kind of data sources do we need to test our ideas? We kind of all agree that water is this critical component. So how do we test that idea that water is critical for lightning? So by the end of, and this was a very quick overview of lesson 1, we're ready to navigate to the next lesson. So what we accomplished what we needed to in lesson 1. We observed an anchoring phenomenon that's going to drive a lot of questions about that phenomenon. There's going to be a lot of questions about lightning. You've already thought about many things you can do to start answering the questions, and you're going to take a minute to take stock of what you've learned so far. What have we figured out now? And what should we do next so that we can figure out our questions that we identified on the driving question board? That in a nutshell was lesson 1. Well, so lesson 1, like all the lessons in the OpenSciEd instructional model, follow the mantra that figuring out, what we do is we figure out instead of learning about every day in class. And there are these 5 investigation routines. So beginning with the anchoring phenomenon, that's what we just did. The lightning was the anchoring phenomenon. We shared that experience, and we talked about what we saw. We have some questions about how it happens, how it works. We develop questions for the driving question board, and then we decide, okay, we need to figure out how to answer some of those questions. Next, we go to the navigation routine. That's where we decide what we need to figure out. Where do we go next? We start planning the investigations for the investigation routine. We know we need we have ideas, we need to collect evidence for them. How do we do that? We do investigations, and we start to be able to explain the phenomenon bits and pieces. Then we put those pieces together and try to come to an agreement on what we've figured out so far. And we figured out, hey, we figured out what lightning is. It's electrons, and they get there through discussion and some support from the teacher. But then there's still other things we haven't figured out, like why is it bad to get struck by lightning? How is there so much energy there? So there's questions we still need to ask. That's the problematizing routine. And then we iterate, we repeat, we try to answer the next question, we investigate, put the pieces together, we understand more, and then we figured out what we figured out, but we also recognize there's more to learn, and we have to answer those questions. And eventually by the end of the unit, we answer the driving question for the unit, hopefully. So there's this logical sequence of lessons that all of this is driven by student questions. So I keep saying PASCO version of OpenSciEd. What is that? So the certified PASCO version is that, well, we took the existing OpenSciEd curriculum and we injected, or we added our technology to it. So a lot of it you'll see is the same, and I'll talk about what is different and what hasn't changed. So we still are, all the lessons are still designed for NGSS and 3D learning. It's still storyline based, like we just talked about with that same instructional model. The units are anchored by phenomena, and the lesson sequences are coherent from student perspective. It's driven by questions, and it is student-led figuring out. What's different? We've added technology, in some cases technology and other products to help just to modify the demonstrations where it makes sense to add the technology. We also updated equipment kits that are available from PASCO that support, that have the technology needed for those changed pieces of equipment. And we've also modified the curriculum so that the directions now work with the technology that we've added. And those resources are organized and delivered in a product called PASCO Portal. So now, what is PASCO Portal? Oh, and by the way, to learn more about OpenSciEd, go to the link. Go ahead and Roger will paste the link in there. So what is PASCO Portal? So PASCO Portal is a teacher-facing resource. So this is a digital environment that supports SSO access for schools and also supports distribution of student assignments through your LMS, like if you use Schoology or Canvas. So you can get the assignments. You don't have to go to a Google Drive to get the assignments, for example, or what if you're a Microsoft school? You can get the Microsoft version or the Google version of the content for the course through Portal. So let's, oh, by the way, we were awarded the Best of STEM pick for Best Digital Ecosystem this year. So that's nice. And you can learn more at pasco.com/portal. So I'm going to jump into Portal and show you what it looks like. And remember, this is a teacher-facing resource. It is a subscription-based resource. And I'm going to answer these questions for you. What resources do you find for the units? And hint, it is the same as the resources that you see for OpenSciEd, but with the PASCO updates in them. And where do I find them? I'm going to log into Portal right now and show you that. So here I am at Portal. Is that showing up on the screen? Yep. Okay. So you'll see that there's a couple of login options here. I am going to log in with my email because I don't have a school system. I'm no longer in the classroom, but you could log in over here. You might see an option that you recognize from other apps that you use. I'm going to log in with my email and it'll look the same regardless of how you get there. So you'll see that I've got some stuff pinned and shortcutted for myself, but I'm just going to go to the main menu so you can see what's here in Portal. We've got an experiment library, which includes all grade levels from K through college and all content areas. We've got curriculum that's not just OpenSciEd, but it's also traditional science curriculum like the essential curriculum and PASCO Academy, which provides support for lab investigations, professional learning for teachers, and support for technical support. And this is also where you would get the software that goes along with the sensor-based investigations. So there's a quick view of what's in Portal, but we're going to let's just look at a unit C2. That's what we're just in at OpenSciEd. So here in my account, I have all 3 forms of OpenSciEd. We were looking at high school. So here's how it works. If I was teaching high school chemistry, I'd subscribe to the high school package. So I would get a subscription to PASCO Portal, and then I would add on the subscription for high school. And the good news is your whole school gets to use the high school package with Portal. So, and the other good news is, even though I'm a chemistry teacher, I get all 3 courses for high school, access to them through Portal, okay, with the subscription. So I'm going to go to chemistry to show you where we were just at here in Unit C2, Structure and Properties of Matter. The question that we were investigating, what causes lightning and why are some places safer than others when it strikes? That is the overview of what we're learning in the unit here. Then the NGSS standards for the entire unit. And then you'll see here, there are some unit-wide useful resources like Communicating Scientific Ways poster, which is often referenced when students are talking to each other and sharing ideas. And then teacher files, let me expand this out. Unit level teacher resources, and a really good place to start if you're brand new at all this and you subscribe to Portal and you're trying to figure out, oh, where do I start? Go to within a unit and then go to the unit overview document. It's a really good place to start. So let's open up that. I just tapped the link there and it brought me into the viewer, and I can get a quick view of the an entire unit document. So let's scroll down to it and see what's in here. I'm going to jump to the overview. Here we have, again, a summary of what we're going to learn throughout all of the lessons. Here's the NGSS standards that we saw previously. Here's the storyline, and this is a kind of a summary of the questions that students will naturally drive towards. Lesson sets, I'll talk about that in a moment, but each lesson tells you how long it takes. So this lesson 1 says it's a 3-day lesson. Also the question that you're primarily investigating in that lesson, and then which of the routines it covers. So the anchoring phenomenon on that storyline routine for here. And then at the bottom, remember we said that continuity and sense making is really important. So down at the bottom here, it says what's coming up in the next lesson to reiterate the continuity between lessons. Then in the next lesson, here's the summary. This is investigation routine. And again, navigation and moving on, tells you how much time each lesson takes. And this entire unit contains 14 lessons, which if you're an experienced teacher would take you 29 days to cover, but longer if you're brand new to all this. So something I also want to point out here is well, hang on. Let's go back out of this unit level document and now look at the lesson specific content. So we were looking at lesson 1, and each lesson has its own little page. within Portal. We were looking at lesson 1, but I'm just scrolling so you can see all 14 lessons are included here. So let's look at the lesson 1 content. There's a description what the lesson's all about and the driving question for that specific lesson. There's that video. Remember we saw that video together? It's right here, easy to get to, all in one place, and more videos that are part of this lesson that I didn't get to. There are student files as well as teacher files separated by who the audience is. I'm going to expand on the teacher files and we're going to take a quick look. There's the lesson plan. So once you understand what the flow of lessons are in a unit, then you'll want to come down and look at the lesson plan for each unit. And this really gives you really detailed information of how to deliver this lesson or how to help facilitate student learning in the lesson. So I'm going to open up the teacher edition in a moment, but I want to point out that there are Google Doc versions and Word, editable Word. So both of these versions are editable, but then there's PDF also that you can click to get a quick view of the document. So here's the lesson plan. Actually, let me back out of here and show you what the Google Doc version looks like. Let's get back to that lesson plan and the Google Doc version. Okay, so here is a lesson plan. If there was a previous lesson, it would say what we learned in the previous lesson, again, with continuity, explaining what happens in that lesson, what's happening in the next lesson, what students are going to figure out, and the NGSS standards associated with that lesson. Then there's this learning plan snapshot, and on the left side in the first column, it says part number, part 1 through, looks like there are 17 parts. So little chunks that you can chunk the lesson up in, but it also tells you over how many days. So parts 1 through 5 is the end up to day 1. And then finally ending at the 3rd day to part 17. So if I wanted to jump to a specific part, like, oh, I stopped at part 3 yesterday, I want to pick up at part 4, I can just jump to part 4 in the little outline. And you'll notice that it tells you what materials you need for that lesson, for that part of the lesson. It gives you some supports for helping students who might have difficulty and need additional guidance, or it gives you prompts, very detailed prompts, sample ways to guide a discussion and sample student responses, alternative activities, and so on. I also want to point out the materials chart here at the beginning of the document. So this is all of the stuff that you need to get the lesson done and where to find it. Notice that a lot of it says PASCO Portal. So that means you just go in there in that lesson and click the titles that are organized nicely within Portal. Or it's something that's in a consumable kit. That's the PASCO kits that I'm going to talk about in a second. Or maybe there's something that you made previously. It reminds you where it came from. Okay, so that's the materials list. And ahead of that, or rather after that, we have the materials preparation section. It tells you how much time you need to get stuff ready and what to do before you begin the unit. Very helpful, especially if you're brand new to the lesson and unit. Okay, so I'm going to go back to the PowerPoint. Okay. Where do you find the PASCO provided materials? So these are available from PASCO. We have classroom consumable kits. So this is something that you would buy one per class per year. It's stuff that gets used up, but it's enough for multiple sections throughout an entire year, and you would buy one again every year. This non-consumable kit, you only have to buy this once for your classroom. And these are meant to last and can be reused year to year. And then there's the group kits. So the group kits, you would buy one per group, and you don't have to purchase these every year. They're non-consumable. But these are the kits that contain the PASCO technology. So for example, pictured here in Unit C2, you'll need a digital balance as part of the kit. And this is a USB rechargeable kit, so no cords. So even the our balance is wireless. This is the water dropper, which I'll talk about in a moment. And this is the wireless current sensor, which we're going to do a sample activity with in a moment. So what has changed with the kits? How is our materials different? So this is the original version of DIY water dropper, and it works. But you'll notice it's on a stool, and you would have to cut these pieces on your own. There's some great directions on how to assemble it and how to do it all. So we did the same thing. We created a document of how to put all this stuff together, but all the parts come pre-cut, all the parts come pre-sized, and everything just fits together. This is actually on a desktop, So you would be doing this on a lab table. So these are the kinds of changes that we made, rather than having to put this on the floor. It's on a tabletop. And you can even see the little drops coming through here. I'll talk about what this is in a second because there's an animation of what it is and how it's related to the lightning phenomena. Another example in the same unit of something that was changed. This is the way that students would measure charges in lesson 13, looking at what is the effect of putting salt in water and what does it have to do with charges. So there's a current sensor here, and there's a digital readout here. Ours is similar. However, the sensor that we use paired with the software, which comes and is included in a Portal subscription, SparkView software, this is a digital display, so it can be either used on a student's own smartphone, you can use it on a tablet, you can project it from your teacher computer and all the students can see it because it's software. And it's also has the ability to record and do graphs and do much more than I have time to show. And in fact, the only type of data we're showing today is digits data, but SparkView is capable of so much more. So if you really want to take your students to the next level with data collection and analysis, you can. But we've set it up to match what the original version does, just with our technologies. Okay, so here is that whole 14 lesson storyline. They're organized in lesson sets, and lesson set 1 and 2 kind of combine to answer the question, what causes lightning? And lesson sets 3 and 4 combine to answer, why are some places safer than others when it strikes? This is the 29 days of instruction length of time. So by the end of lesson 1 and kind of what we went through is we agree that water is there. We've come to agreement on that model. Water is present when lightning occurs. So we study a model of lightning. We actually create sparks, which is a mimic of lightning. And we find out that there are forces around parts of the system, and there's attractive and repulsive forces. So let's take a look at that system here. Here it is in action. It's an animated GIF, so we can see that water is dropping down through these metal containers on either side. And while that water is falling through these metal cans, there is a little bit of charge, well, more negative and more positives just by chance on one side or the other. And that just gets exacerbated. It gets really, the metal helps it really shift over to one charge or another. And when that happens, let's say that this side becomes positive, you notice the wire is connected down here. So that also becomes positively charged, and the water coming down is now negatively charged. So if this is negatively charged, it's hooked up to this part over here, which is also negatively charged. So we have this charge separation occurring. And this is actually a model of what's happening with lightning. Students don't need to know all of this yet. All they need to know is, hey, I get this piece of tinsel and I bring this tinsel close to parts of this model into the system. And I notice that I have to get kind of close, but suddenly the tinsel just kind of does this on one part of the system, but then on another part of the system, the tinsel just does this. So there's this opposite action. And by doing these tests, they notice that there are these forces that are around the parts of the system. And you don't have to be touching the system to know, the matter does not have to touch to know that there's some kind of force there. So by testing all these objects and how they interact in the spaces between the components of the system, they figure out that there's got to be something moving among those components. What's that invisible thing? And they do a whole bunch more of hands-on investigation and discussion and reading and simulation. And by the way, this is a zoomed in portion of the spark. So basically this is the water dropper, and this little spot right here that you can barely see is zoomed in. There is a spark that occurs through the middle of air, in between air. We get the spark between these two electrodes, and that's kind of like lightning. We get this big spark and that comes through air. Why does that happen? Well, we now have a little bit of evidence. We now know something we didn't know before. There's a force somewhere around those parts of the system, and we just take that and run with it. So, and they do more hands-on activities to experience forces and static forces in other ways, and then also model matter or particles with components that make up matter. So we start talking about, eventually we get our way to subatomic particles and models of the atom. So what do we get out of this lesson set? Students develop an atomic model based on evidence from investigations and research. And they discover that electric fields and forces do exist, and the distance matters. The closer you are, the stronger those forces are. But we figured those things out. We actually figured out the lightning is electrons, something charged, but we still don't know how those electrons can move fast enough to create that lightning bolt. So that question is driving our next lesson set. What causes a lightning strike? So we learn in this lesson set that the collisions, when a thundercloud forms, the collisions between the air particles result in a charge separation. And that's how charges build up in clouds and opposite charges. Um, so that eventually the charge has to flow to the ground. And with more and more investigations and discussions and research and simulations, we further developed that lightning model, and students do an investigation where they figure out Coulomb's law. They quantify the force of electrostatic interaction using charge and mass. Students explore ideas around induced polarization, and then there is something called a transfer task. So students figure out how matter is significant for lightning to form because those particle collisions are required. Matter has to strike one another for the charge separation to occur. And they also know that the forces are significant because attraction and repulsion, that's what allows the charge separation to happen. But the students have studied matter and force, but not quite energy yet. And now, before we move on to that next idea of energy, you've got to make sure that we really got a good handle on matter and forces. And that's where the transfer task comes in. So the transfer task is it's like a summative assessment, where in this case, students are observing some similar phenomena. It's not quite the same, but it's similar, where it's like static charge, like taking a neutral glass rod and rubbing it with, charging with a piece of silk. And then students see what happens, they observe behavior, and they should be able to explain that new phenomenon they observe based on what they've learned about the lightning phenomenon through all their investigation thus far. So moving on then to the next lesson. So now that we know what causes lightning, now we can start looking into why are some places safer than others when it strikes. So we confirmed that lightning's energy source is the electric field created in the clouds. We've confirmed, or we've used simulations and their models to investigate evidence of energy transfer. Sound and light are the evidence that we notice. And we explore the ionization of air molecules. So in this lesson set, we're also figuring out that when an electric field is strong enough, it can rip electrons off nearby air molecules. And these ripped ionized channels of air, that's what branches out. That's the path that the electrons move through. That's how they get through so quickly and produce that bolt of lightning that we see. So we know a little bit more about lightning, but we still don't know why are some places safer than others. So we're driving now to the next lesson set, where students apply everything they've learned about subatomic particles, charge, energy transfer, and they use that to understand why different materials, like the lightning rod on an airplane and conductive gel in a medical device, why those properties and the property of conductivity, why those are different for different types of matter. So we're going to explore lesson 13. Notice it's only lesson 12 through 14 here. We're going to explore lesson 13. Students would have also be doing more hands-on, more literature-based data analysis to learn that metals have free electrons, and that's what makes them good conductors. That's just some additional content that they look at to learn. But it's them driving, it's them figuring it out. It's not the teacher saying what it is. So let's, and then after we look at 13, we're going to talk quickly about what the transfer task is for this. Okay, now another phenomenon. So the strange thing happened in the St. Lawrence River, which is in Canada, on the eastern side of Canada, kind of near the Great Lakes, dividing the US and Canada there. These geese, and this is a picture of the region, these geese all turned up dead. A whole bunch of geese died. And there was an article in the paper that said something about it, and students are given that article. It's a very brief article. Geese lightning strike, the mysterious death of 50 Canada geese outside of Montreal. Here's the St. Lawrence River right here. And this is where it occurred, just around Montreal. 50 Canada geese were found dead floating in the St. Lawrence River, which flows from the Great Lakes to the Atlantic Ocean outside Montreal earlier this week. Local veterinarians are saying they may have died from electrocution. A local fisherman came across the geese near Contrecoeur, Quebec, Canada, on Thursday. Veterinarians were called in from University of Montreal to examine the bodies. Veterinarian Stefan Lair said that the geese had small lesions in their hearts. Wow. And indicated possible electrocution. He said the level of decomposition indicates that they all died at or very near the same time. The students read that to themselves. Wow. And then we wonder, what happened to the geese? So we kind of introduced another kind of anchoring phenomenon related to the lightning. What happened? Now, everybody on the Padlet, some ideas, please. What would you like you to think? I'd like you to think about what happens to the electrons. We know that lightning is electrons. What happens to the electrons that are in this bolt as soon as they reach the water? We know what happens on the ground. What happens on the water? What do we think happens to the electrons that flow out of the cloud once they reach the surface of the water? Please go to Padlet and share your ideas. So you already know, we did all those lessons before. You've got this understanding. You know that electrons is what makes up lightning. You know, it's transferred to the ground, but what about water? What about water? Why is water dangerous? But actually the question is, what do we think happens to the electrons from the bolt once they reach the surface of the water? Just started. What do you think? Okay, I'm seeing some people type in. They spread out across the surface. Maybe they move into the water. Oh, that's great. Lots of question marks. Question marks are important because we always recognize that we're continuing to develop our knowledge and we're not sure. We want to indicate that with a question mark. We're not sure. Electrons go across the water surface. Maybe they move into the water. So they got to go somewhere. I mean, that's what lightning is. It is electrons. What happens when it gets to the water? Wow, fancy parrots, pretty fancy. The bolt rips electrons away from water molecules to form a channel in the water. Channel, yep, we learned, right? We learned about the ionization channels. They form a channel in the water and then they can flow into it. So that would suggest that water, like air was able to ionize, and that's where the electrons move. Maybe water can do the same thing. Maybe. I don't know. I don't know. Let's investigate. Okay, so now let's think about this. I'm going to present some data here. Everybody would think on their own. Here's some data about water sources. Distilled water has no salt in it. Drinking water, percentage-wise, has 0.1% of salt. Lake Michigan water, which remember that's going to be near the area that we just looked at, really small percentage of salt, less than 1%, less than 0.1% even. It's even less salt than drinking water. Wow, amazing. Ocean water. Now we're getting up into digits here. So 3 to about 4% of salt in ocean water. Pool water, up to 4% of salt. So if we were to investigate how much salt there is in water, does it have anything to do with what happened to the geese? We might want to know what percentages are normally encountered in real life, like in a lake or in an ocean or in a pool. And that'll help us design an experiment where we can test our ideas of how does salt affect the ability of those charges to move from the bolt to the water? What happens as soon as those charges hit the water? So cutting through a bunch of, going to a shortcut here. Now students can plan an activity, and we're going to investigate water conductivity with the charge sensor, or rather current sensor, not charge sensor. So in order to do that, we need to go to Portal and download a file that's included with the contents of the course. So I'm going to go to that course. Remember, we went to curriculum, to OpenSciEd. We're in the high school. I had to close my window and I forgot to leave it open. And go to the chemistry course. We were in C2. Now we're in lesson 13 though. So I'm going past the unit and going down to lesson 13. Here is where we get the file for the investigation. It's just in the resources. And by the way, student files. So it's a student-facing file. We need to share it with students, so you'll find it here in students. Again, editable forms of the contents here, but also Spanish versions for students. We got Google Doc form, PDF, and Word doc forms. So there is a file for doing the SparkView activity. So I'm going to download it. And now that I have it in my downloads folder, I can open it. And that will open SparkView. And SparkView is a software that comes with a Portal subscription. But there's also a web-based version that you can get in a browser. And I'll put that up in a moment. Let me make that small. Okay. So there's that SparkView file. We'll come back to it in a second. If you go to pasco.com/SparkView, you can get the web-based version of the software. And when you go to Portal and you go to the software help and downloads page under support, that's where you get the software. And it also explains how the software works with each of these devices. So whatever you use in your classroom, there's a SparkView that works. And you can read about it at pasco.com/SparkView. We just downloaded this file. Remember, it came from the student assignments because it's something that would be shared with students because students would need to have their own on their own device. So whether you're using the version that you download for Portal or whether you go to the SparkView web version, they're going to look the same. The only difference is in the way that the sensor connects. Otherwise, it's going to be the same. So now there's a teacher demonstration, and I'm going to bring just this up. So I'm going to switch cameras, and you're going to see the setup. So I'm going to connect this system, and what I want to explain is this device can measure the charges traveling through any part of the system that's connected with wires. So let's think back to the water dropper. We had this system where we had wires that were allowing charge to be transferred from one part to another. So if we start, this is our source of energy is the battery. If we make charges flow out of the battery, let's just pick one direction. Let's just say it goes this way. If I start energy coming out, let's say it goes through here, through this wire, I'm tracing it all the way through. Oh, look, that light lights up. So I can see that there's evidence of electricity reaching through the light, and I know it's going through here. And this device helps me measure how many charges, or the amount of charge, current, that is flowing through these connected wires from the battery. So let's turn on the sensor and connect it to SparkView with the Bluetooth icon. Tap to connect. Okay, and start collecting data. There are 228 milliamps of current running through this. Okay, so let's keep that in mind, like 200 something, right? So now I'm going to undo it. Now, at this point, you'd ask students, well, and by the way, I'm leaving SparkView running because that's fine. I can just keep running. Well, how do we test whether the charges went to the water? You'd have to modify this system, this setup here. So let's do this. Let's put some, distilled water. That's the purest water we can get. Let's see if we can connect the system, the path through some metal. Remember, we learned that metal is a good conductor. So if energy or electricity or electrons are flowing, the metal will allow it to come through. Let's test and see if we can get the water to flow through. Water should be able to put charges through it, right? Like air can do it. Why can't water? And we have continuity. We have, oh, well, maybe we don't. Okay, so I've got water's supposed to be dangerous, but the light's not on. Well, wait a minute. Maybe it has to do with the type of water we have. We had lake water, right? It still says 0 milliamps. We had lake water, and lake water, if we back up, is somewhere between here and here. Percent of salt. Distilled water doesn't have any salt. Oh, okay, well, salt's important then, right? So if salt's important, let's test salt. Okay, I forgot my paper towel, so I'm gonna dry this off, sort of. Let's test salt. All right, I got all this salt. Awesome, that should be able to transfer charges because that's, oh, that's also not working. I don't have a light on and I have 0 on my current measurement. What the heck? Maybe both have to be there. Maybe it has to be salt water of some amount. So let's add some salt to the distilled water that we had before, stir it up, mix it, and now let's see. Ah, yes, the light is on and we have current. So, wow, salt in the form of a solution is necessary to get current to flow. What does that mean? Let's see, does the amount of salt matter? Let's design an experiment. At this point, this is where students would work with the Coulomb's law. They figured out what the constant is. They figured out in a previous lesson. Let me undo this. That 1 milliamp of current is or they figured out that the constant for Coulomb is 6.24 times 10 to the 15 charges per second. So the conversion to current, which is what's just coming out of the sensor, is this value. So they could either write it as a fraction 1 milliamp per charges per second or charges per second per milliamp. So we had 200, let's just say it was 225 milliamps, and you would go through the calculation with students and convert. It's capital A. And convert the current sensor value to determine the charges per second that each salt solution forms. And students would plan their own experiment and would test different amounts of salt. So the light would be different. Because I'm running out of time, I would normally rinse these between solutions, but I'm just going to skip that step. They would see that the value of current is lower when the light is barely dim and the percentage of salt is really low. And they would note, and they could also calculate the charges per second running through each solution. And here's a 3% solution of salt. That first solution was 0.5%. Students would decide what percentages to use, and they can use that table to help them determine. And there's 3% salt. So I forgot to hit start. There it goes. Look, that value wasn't changing. So we have slightly higher milliamps of current and slightly brighter light. So student get the idea that concentration affects the electric current or number of charges flowing through the path per second. Okay, all right. So here's what the handout looks like. Students can use it digitally, or you can print it out and have them plan the investigation and put in their percentages. And you can walk through the calculation. And we use percentages because students remember that the density of water, they learned this in Unit 1, is 1 gram per milliliter, and they can easily calculate if they make 100 milliliters of solution, it's very easy to do the math to get the percentage or the grams of salt that you would add to the grams of water to total 100 grams to get the percent. So would suggest not go over 8%, probably stay within the range that we're in the table. And then here's the conversion factor for current. Okay, so students would then go back and tie what they learned. What does the matter that made up the salt go? Where does it go when it dissolves? If the particles that make up the salt are all together and we can see it, when we put it in solution, we can't see it. What happens to those particles? They come up with the idea of the ions forming, just like we talked about in air with the electrons leaving and the electrons moving from, here's that same model, electrons moving from the sodium to the chlorine, and now we've got ions. And we figured out that the salt in the water helps explain why electric charges can travel through water. We also have salt in our bodies. Why do we have salt in our bodies if it's something that can electrocute us? Well, students then learn through reading why ions are so important for life, from the cell level all the way up through organ systems. So now we're bringing biology in. Eventually, the consensus model, here's an example of a fully, at the end of the unit, complete consensus model with everything, all the understandings of the biological, physics, forces, matter, and energy all together. It's the system. We understand now how lightning works and why it's not safe to be in water with ions when electricity gets delivered to it. And we can explain what happened to the geese. So we come to the end of the unit assessment. Now we're ready for the transfer task. So there's two parts to it. The first part is how does the lightning rod on an airplane work, a radome? How does that work to not only protect the humans inside, but also the electronics? And then part two, the gels, use it for medical technology. These gel plates, how do they work? How do they protect us but also heal us? What about the body and chemistry and physics all together? So the unit overview document, there's a whole bunch of assessments from formative to summative, and that unit document I showed previously gives you an idea of what they're like throughout the entire unit, and even goes into lesson by lesson detail. There's also a grading planning tool that you can fill out. Here's an example of one filled out for the whole unit, and you can decide how the points should be distributed throughout the unit. Now, if you want to learn more about either PASCO's version of OpenSciEd for middle school or high school, there is professional learning available on PASCO Portal by subscription, obviously, um, by subscription. So there's also some video tutorials, so you can go through courses and get a certificate, or you can watch quick videos to get you through quickly. But if you want more on the OpenSciEd model itself, just that, we've paired with better lessons so that you can get the level of specificity that you need, whether it's live virtual workshop or something online like this. So to learn more, please contact your regional rep at pasco.com/support. And also, go ahead and try out Portal for free for a limited time. Just scan that QR code or go to the link and get a free trial to PASCO Portal so you can see what it's all about with OpenSciEd and all the other goodies that are in there. Okay, so if I'm going too fast, you can go ahead and pause that when you get the recording. And with that, we're going to wrap up here. And thanks for watching. Thank you for attending.